so we can get started with the poster. Just a second. Okay, so good morning, everyone. My name is Vishnu Suresh, and today I'm here with my colleague Dominika Kaczorowska. I currently work as an associate scientist at Hitachi ABB Power Grids in Poland, in Kraków, and my colleague works as an adjunct professor at Wrocław University of Science and Technology. So we would like to present a poster about our paper, Energy Savings Approach to Optimal Location of EV charging stations in a microgrid. So basically, it's with regard to microgrid planning and microgrid economic dispatch. We have a model that is partly based upon the microgrid model available at the university. So the load data that we used is in fact measured at a nearby village, and we scaled it to our needs. The data that we take from the solar panels that is installed in the microgrid model are in fact from the panels that are in the rooftop of the faculty building. And in the poster, the first figure is in fact about the layout of the microgrid. So basically there are like 5 nodes with different distributed energy sources, a storage system, and a diesel generator and an electrical vehicle charging station. So the main objective of the work was to identify proper charging and discharging, not discharging, charging control of the electrical vehicle charging stations. So basically what happens is the rate of charging is basically determined by the energy management system of the microgrid. And the main objective function in this case was to simply minimize the power that is taken from the main grid so that the system in overall remains self-sufficient to the maximum degree possible. So in order to have a comprehensive study, we decided to cluster our data. Basically, we had yearly profiles of the data from the solar panels, from the load, etc. The optimum number of clusters for this kind of data was 3 clusters. The method we used to find the optimal number of clusters was within the cluster sum of squares, and the number came out to be 3. And we saw that there is a correlation between the number of clusters and actually the kind of season that we usually observe in Poland. So here I have 3 figures which shows the generation and the load data for the different clusters. So the second figure on the poster is basically very characteristic of the load and generation profile during the spring and the autumn, during which the generation and the load demand is actually quite close to one another, but sometimes the load is a little higher, as shown in the figure. And of course, in Poland, it's actually a very beautiful time, the autumn. And the next figure is like the generation profile and the load data during the winter times. During the winter times, it's actually quite dark here in Poland, and we can clearly observe that the amount of power generated within the microgrid is in fact quite low, and the load demand is much higher. So during these times, the power that is imported from the grid is actually quite high. And in the next figure representing the next cluster, we see that the generation is actually much higher than the load, and this is usually during the 2-3 months of summer, during which the solar panels are actually working quite close to their rated capacity. So now, given these profiles, the main objective is to find in which node within the microgrid layout is the most optimal place to have the charging station, because the total number of nodes are in fact 5. So the approach, in fact, we used is to just cycle the electrical vehicle charging station across all of these nodes, and then to see which place is the most appropriate. And as I mentioned before, the one of the most important features for this charging station is about controlling the charging. So there are basically two modes in which the charging of the vehicles is controlled, and in another case when it is uncontrolled. So in case of an uncontrolled scenario, basically the chargers charge the vehicles at the maximum capacity possible. So in fact, there is a figure in which the load in the microgrid is shown under these two cases. So in case of uncontrolled charging, we can see that the curve is very random, and there are too many peaks and too many falls in the load demand, and which that is definitely not something that we would prefer. But in case of a controlled charging, you can see that the curve is more smooth, and it is better to have such a scenario. And also another figure on the bottom, this figure basically shows how power is being exchanged with the grid when we use controlled charging and uncontrolled charging, and it can be seen that it has a characteristic similar to that of the load, where the power that is taken from the grid is just increasing and falling at a very rapid manner, and in case of the controlled charging, it is quite smooth. And it is also in fact possible to track the state of charge of the different electrical vehicles that come into the charging station, and that is the final figure. The charging station has a total of 5 chargers, but we took the data only from 2 chargers. And in fact, when a car is charging, we see a kind of a straight line. So, and once it is charged, the vehicle departs, the curve falls down, and then it comes back up when the next vehicle comes to the charging point. And we look at the total energy savings done by examining data on all the 3 clusters and choose the ideal location within the microgrid. So that is what this paper is about and this poster is about. So, any questions? I cannot hear. I cannot hear if someone is talking at this moment. What happened? It's here on chat. Okay. Okay. How do I stop sharing this?
Hello? Okay. Can you listen me? Pero no me contestan. Hello? Hello, can you listen me? No me Yo creo que no me oyen ellos. Sí. Thank you for the presentation. Now we are going to begin with the questions. Does anybody any question in this moment? Pero no. No questions. Okay. So we finish with this presentation and we pass to the next poster presentation. Thank you very much.
Hi, my name is Iron. I am a master's student at Federal Institute of Goiás in Brazil. Today I'm going to present a poster of an article entitled Synthetic Series of Electricity Generation through a Photovoltaic System by using different panel temperature models. This work is part of my master's research and compares three temperature models of photovoltaic panels and electricity produced from a photovoltaic system located in the Midwest region of Brazil through the evaluation of expected average and standard deviations. The results indicate, through a stochastic analysis, the model that best describes the physical system in relation to photovoltaic technology, location, and measurement values. Photovoltaic solar energy is the fastest growing energy source in the world. The electrical energy supplied by photovoltaic panel is a function of the solar irradiance and the model temperature. There is great difficulty in predicting the energy generated by photovoltaic systems. Panel temperature and power output depend on several stochastic factors such as solar irradiance, ambient temperature, wind speed, humidity, and wind direction. Panel temperature can be predicted by several models. This work compares the performance of the models presented by Masters, Pinheiro Neto, and Talismani from a stochastic perspective. This study aims to fill the gap in the small number of studies that consider the random variables to estimate the electricity generated from photovoltaic systems during the project lifetime. The flowchart of the methodology used in this work is shown in Figure 1. We enter with the historical data, then we obtain the stochastic model for each random variable from the pre-processing and validation of the models. We then generate the synthetic series of random variables that will predict these variables throughout the life of the project. We then use the synthetic series of the random variables to estimate the panel temperature using the different panel temperature models. Then, from the data from the photovoltaic system, we calculate the power and energy generation of the photovoltaic systems. Here we have the autoregressive stochastic model to describe the random variables. Data preprocessing is performed by pulling out the trends. Model validation is done using the mean relative percentage error. Here we have the panel temperature model's equations, and here we have the power generation model. Historical data of solar irradiance, ambient temperature, wind speed, humidity, and wind direction was obtained from the National Solar Radiation Database for a photovoltaic system installed at Itumbiara IFG campus. In Table 1, we have input data from the photovoltaic system. Table 2 presents the estimated parameters of the AR model for each variable. AR parameters were estimated using the maximum likelihood method. It was generated 2,000 scenarios of the synthetic series of the random variables for the entire period of the historical data, which was 20 years. Then, historical series and synthetic series were compared with each other in relation to their average, standard deviations, minimum, maximum, and the mean relative percentage error. In figure 2 and 3, we have the validation of the synthetic series with the average of the historical data. Table 3 presents the statistical parameters of the synthetic series for each variable. Figure 4 presents the measured and calculated temperature of the panels using the different temperature panel models. The values of panel temperature measurements were obtained from January 17, 2018 to April 16, 2019, corresponding to 16 months. The mean percentage error from panel temperature calculated using models A, B, and C with the measured panel temperature are 5.73%, 4.67%, and 3.77% respectively, as we can see here. Figure 5 and 6 present the monthly and annual average and standard deviations of the energy generated for each temperature model. The decrease in generated energy found in Figure 6 is due to the degradation of the panel's efficiency over time. Conclusion, we used the autoregressive model to predict the random variables solar irradiance, ambient temperature, wind speed, relative humidity, and wind direction over the project lifetime. We then used the prediction series to estimate panel temperature and power generation using the different panel temperature models. Panel temperature measurements were also performed in a photovoltaic system located in the city of Itumbiara, in the Midwest region of Brazil. The results indicated that the model that came closest to the measurement data was Model C. This work aimed to analyze the panel temperature models from a more precise perspective and can be used in risk studies, as in the economic feasibility analysis of photovoltaic systems. These here are the references used in this poster, and thank you. My name is Iron. I am a master's student at Federal Institute of Goiás in Brazil. Today I'm going to present the poster of an article entitled Quantification of CO2 emission reductions from energy efficiency actions and solar photovoltaic generation at the Federal Institute of Education, Science and Technology of Goiás. A research and development project was implemented at IFG campuses consisting in efficiency actions and photovoltaic distributed generation. This work aims to quantify the CO2 emission reduction from this project. The emission reductions over the project lifetime was estimated at approximately 39,796 tons CO2 equivalent, evidencing the environmental benefit of this kind of project. They implemented the research and development project entitled Energy Efficiency and Mini Generation in Public Higher Education Institutions was executed between April 2018 and May 2019 on 12 campuses of IFG located in the cities of Goiás State, as illustrated in Figure 1 here. The energy efficiency action was the replacement of the fluorescent and sodium vapor lamps with LED lamps. The photovoltaic system consisted of approximately 1.255 megawatts peak of installed capacity. Figure 2 shows the flowchart of the methodology used to quantify the emissions reductions of CO2 equivalent from the project. For the photovoltaic power generation was used AMS-1D methodology from CDM, and for the energy efficiency actions was used AMS-2C methodology from CDM. AMS-1D is grid-connected renewable electricity generation version 18, and AMS-2C is demand-side energy efficiency activities for specific technologies version 15. Now I'm going to present the equations used in this work. The total emission reductions was calculated through the sum of the emissions reductions of photovoltaic system and energy efficiency actions. Emissions reductions from energy efficiency and photovoltaic generation was calculated through baseline emissions minus project emissions minus leakage emissions. Baseline emissions from the PV project was calculated through the energy generated multiplied by emission factor of the electrical system. We have other equations used in this work, such as the emission factor of the electrical system, the baseline emissions from the energy efficiency actions, the baseline energy consumption, the project emission consumption, the energy consumption after the implementation of energy efficiency, and the project emissions from the physical leakage of refrigerants. It was considered the emission factor as the average value from 2012 to 2018 equal to 0.4811 tons CO2 per megawatts hour. The energy efficiency action was the replacement of the lighting system consisting of fluorescent and sodium vapor lamps with LED lamps. It was installed 3,850 photovoltaic modules of the polycrystalline type of 315 watts peak and efficiency of 16.68%. Figure 3 presents the power generation of PV system at IFG. Figure 4 presents the avoided CO2 equivalent emissions of PV system in IFG. Table 1 and 2 present the existing and proposed lighting system of the campuses. Figure 5 presents the project emissions reductions throughout the project life. Over the project lifetime, the total emission reductions range from 1,666 to 1,522 tons CO2 equivalent, and the total reduction was estimated in 39,796 tons CO2 equivalent. The project included the replacement of the existing lighting system and the installation of PV system totaling 1.255 megawatts peak. The results presented in this article show the environmental benefit of CO2 equivalent emissions that are no longer released into the atmosphere. It is possible to cease the release approximately 39,796 tons CO2 equivalent into the atmosphere, with 19,905 tons CO2 due to the implementation.
Can you hear me? My name is Julia and I'm from University of Politecnica and from Power Engineering faculty, and I will present the particularities of high oxygen content biofuels in pyrolysis process. I am here with my colleague Emanuela Grigoriu, and I will start talking about that this research is regarding the efficiency of conversion, thermochemical process conversion. The paper addressed to the particularities of high oxygen content in biofuel pyrolysis. It's about the oxygen which represent an undesirable internal content, and our experiment is made with poultry manure, which is mixed with some biomass flooring from bird house, but they have the same energy characteristic to the waste. We know that the pyrolysis process is simple process of converting, and the calorific value of the fuel gases is range between 7 and 40 megajoules on cubic meter, normal cubic meter. In this table, we have some other biomass types. Other particular aspects of pyrolysis technology. Here we have a figure with pyrolysis technology, or a model of our installation, which is analyzed in this experiment. Some other characteristics of biomass is the max of volatile is reached, the content release is reached in a range between 380 degrees Celsius and 550 degrees Celsius. From the beginning, it's necessary to reduce the moisture content. From this, we have the temperature for inlet, and which is present by T1, and temperature for outlet, which is T2. For drying is required the quantity between and Q2. From fuel B1 is eliminated from content of B1 is in this phase is eliminated the moisture. In pyrolysis zone, from fuel 2, the volatiles are eliminated and result the cokes. For high content of oxygen is recommended to use semi-pyrolysis process because the low temperature cannot conduct to bioxide of carbon oxidation. After internal combustion, the carbon cannot be deterred. Conducting semi-pyrolysis experiment maximum temperature of 550 degrees Celsius on poultry manner led to results. Moisture removed, volatiles including carbon oxide from the internal oxidation became 0.5 kilo, and the coke became 10% from fuel content. Compared to the fixed carbon that had a value around 0.43, the semi-coke decreased significantly. Conducting an element analysis of the semi-coke in mixture with ash resulted in obtain 9,481 calorific value kilojoules on kilogram. So I will finish with some this presentation with some conclusion. The paper is address the carbon oxidation in biofuels during the pyrolysis process. For the low temperature pyrolysis, the oxidation lead to the formation of oxide carbon combustion gas, which is added to the volatiles. Instead of high temperature pyrolysis, bioxide carbon will form so that the oxidized carbon will lead to energy loss. Pilot scale research facility to allow temperature pyrolysis process of poultry manner has emphasized the above mentioned issue. The reduction of the final quality of coke or semi-coke evaluated up to 7. Okay, thank you. Any question?
Can you hear me? No. No se oye. So we finish the poster section, this first part of the poster session, because we don't have more time. Thank you very much. Y ahora se ponen los otros vídeos, ¿no?
Hello everyone, my name is Priscilla and I will present the paper entitled Investigation on Low Voltage Automatic Regulation to Minimize the Impacts of Charging Plug-in Electric Vehicles in Distribution Systems. With the encouragement of decarbonization policies, there is a growing penetration of electric vehicles (EVs) in the global automotive market as a more sustainable alternative to conventional internal combustion engine vehicles. However, the expansion of electric mobility presents challenges for operators of electrical power as the main contribution. The potential usage of automatic low voltage regulation (LVR) was investigated to minimize the negative impacts of uncontrolled plug-in electric vehicle charging on distribution systems steady-state operation. 4 scenarios are considered. The base scenario, there was no plug-in electric vehicle allocated in distribution systems. The PL5, 15, and 35% scenarios, there were 5, 15, 35% of customer units with allocated plug-in
We'll start with paper 240. The title is Design of Power Quality Virtual Lab.